In this video, I'll be discussing the life, work, and psychological contributions of Donald Olding Hebb. Hebb was born on July 22, 1904 to Mary Clara Hebb and Arthur Morrison Hebb. Hebb was the firstborn child of four. Both Mary and Arthur were medical doctors in Chester, Nova Scotia. Hebb's mother, Mary, was the third woman in the province to become a medical doctor. Hebb's mother was a religious individual and took Donald to church every Sunday. At an early age, Hebb accepted the scientific mindset and began questioning religious teachings. This questioning likely resulted from the vast knowledge he already obtained from reading numerous books. Hebb's mother died early, when Donald was only 17 years old. This would prove traumatic for him and inspire him to continue hard work throughout his life. Hebb was married 3 times, his first 2 wives passing away at an early age. With his second wife, Elizabeth, Hebb had 2 children, Mary and Jane. Hebb passed away August 20th. Donald's mother homeschooled him until he was 8 years old. Once Hebb began attending school, his intelligence passed that of other students quickly. He became bored with school because, again, of the high volume of reading he engaged in prior to attending school. Because of his boredom with school, he did not learn how to complete work thoroughly and failed a few subjects. Despite this, he graduated high school, excelling in math and physics. Following graduation, Hebb earned degrees in philosophy and English. Shortly after earning his degrees, Hebb joined the workforce as a principal and high school teacher. Hebb left his job as principal and moved to Western Canada to work as a laborer. After failing to work as a laborer, Hebb applied to earn his master's degree from McGill University. Hebb believed the only reason the school accepted him was because his mother knew the chair of psychology. Shortly after Hebb received his master's degree, he married his first wife, Marion Isabel Clark, who died 18 months later from injuries received in a car accident after her and Hebb had an argument. She died 2 days after the accident, on Hebb's birthday. The accident ruined Hebb's car, and he had no way to continue his research. Because of this, Hebb moved to Chicago to complete a doctoral program in psychology at the University of Chicago. During his time at the University of Chicago, Hebb worked closely with Carl Lashley, who became Hebb's mentor. After only 1 year at the university, Hebb requested Lashley take him to Harvard. Since Lashley accepted a position at the university, Lashley agreed and Hebb received his doctoral degree from Harvard in 1985. As I stated earlier, Hebb began his working life as a high school principal and teacher before attending graduate school to earn his master's and doctoral degree. After earning his doctoral degree, Hebb moved to Montreal, where he became a fellow of the Montreal Neurological Institute. While in Montreal, Hebb married his second wife, Elizabeth, and became a father to 2 daughters, Mary and Jane, as I stated earlier. Hebb then moved to Florida to rejoin Lashley and study chimpanzees. Until 1940, Before moving to Florida, he did work for a short period at Queen's University in Kingston, Ontario, where he began writing his research that inspired him later on at Yerkes Laboratory with Carl Lashley. After working with Carl Lashley to study chimpanzees, personality and emotion, he received a professorship at McGill University. The psychology program at McGill University was relatively non-existent, and Hebb began his work starting a true psychology program. During his time as a professor at McGill University, he served as the president of the Canadian Psychological Association and American Psychological Association. Hebb was the first foreign-born president of the American Psychological Association and received the award for a distinguished scientific contribution in psychology from the American Psychological Association. While he was a professor at McGill University, he was promoted to become chancellor of the university. He was the first faculty member to become a chancellor and served from 1970 to 1974. As I stated earlier, Hebb wrote a theoretical paper at Queen's University, and in this paper he discussed learning in infancy and how the frontal cortex plays a major role. This theoretical paper played a major part in his book, The Organization of Behavior. In his book, Hebb describes the functioning of neurons in learning. The functional learning theory of neurons he described in The Organization of Behavior is now an established psychological concept known as neuroplasticity, a concept too advanced to empirically test during the time of his book's publication. His theory, appropriately named the cell assembly theory, gained popularity in a time when behaviorists dominated psychology. Hebb utilized the works of prominent psychologists such as Carl Lashley to support his theoretical claims. Hebb acknowledged his theories would need revision as the psychology community advanced its understanding of the neurological phenomenon, but the majority of his theory remains intact and gains support with advancements in neurology. The cell assembly theory is the neurological basis of understanding of learning in psychology. In the cell assembly theory, Hebb explained neurons influence each other when forming connections. For example, the locations of neuron A, neuron B, and neuron C in the same area of the brain. All three of the neurons, dendrites, and axons interact. Because neuron A receives more external stimulation, the rate of neuronal firing increases. The location of neuron A is closer to neuron B than to neuron C. Since neuron A fires more, the interaction between neuron A and B is greater than the interaction between neuron A and C. This leads to a decrease in the connections between the dendrites and axons of neuron A and C, and an increase in the connections between neurons A and B. The number of connections affects the firing rate of the second cell and the continuation of active potentials. Although neurons A and B interact, the stimulation of neuron A may not be large enough to stimulate an action potential in neuron B. Too few synaptic connections between neurons A and B means neurons A's action potential cannot elicit neuron B's action potential and vice versa. The explanation of this phenomenon exists at the synaptic cleft. Neuron A may only have 4 synapses with neuron C, but neuron C requires 6 synapses to elicit an action potential. Thus, neuron C does not fire. The release of Hebb's book, The Organization of Behavior, was successful and the field of psychology generally accepted his ideas. Although Hebb had not tested his landmark theory regarding the neurophysiology of learning due to technological restraints of the time, the fundamental theory between his ideas followed logical scientific evidence. Today's scientific community accepts Hebb's postulate as scientific fact and named synapse after Hebb, the Hebbian synapse. When Hebb proposed his hypotheses regarding the synapse, he could not elaborate extensively upon how they work. This was due to the lack of technology available to explore something as small as the synapse. For many years, researchers could not investigate Hebb's claims due to the aforementioned restraints. In the last 40 years, technology advanced to a point where researchers could investigate the synapse in depth. The advancement in technology allowed researchers to expand upon Hebb's original hypothesis by investigating the dendrites. Prior to the advancement in technology, neuroscientists believed the dendrites were a passive part of the neuron that only conducted neuronal transmissions. This changed when researchers found dendrites actively participate in the generation of action potentials through the utilization of electrodes. Levy and Stewart in 1979 investigated the induction of long-term potentiation in the hippocampus of rats by stimulating specific areas of the brain with electrodes that were unavailable at the time Hebb formed his postulate. The researchers found interesting ipsilateral and contralateral interactions between neuronal pathways in the rats. This led the authors to suggest coactivation of synapses within the rat's hippocampus. The aforementioned finding supports Hebb's postulate by demonstrating the interactions between synapses in the brain. Levy and Stewart in 1983 created a second research study investigating long-term potentiation using a similar experiment as their study in 1979. In 1983, Levy and Stewart found temporal relationships in ipsilateral and contralateral pathways influence the induction of long-term potentiation. To further expand Hebb's postulate, McGee and Johnston found the induction of long-term potentiation can result from depolarization of the postsynaptic neuron. Because of this, the authors correlated increases in synaptic strength correlate with synaptic input and action potential output. This led the authors to believe the results may support Hebb's postulate regarding the enhancement. And here are my references. Synaptic strength resulting from an increase in synaptic activity.